We have all been there. You are cruising down the highway, making excellent time. The conditions are perfect. Then, without warning, brake lights. You slam on the brakes, your coffee spills, and you spend the next 20 minutes crawling forward at a walking pace. You crane your neck, scanning the horizon. You expect to see a massive pileup, a police chase, or a construction crew closing 3 lanes. You need a reason for this delay. You need a cause for the effect. But then, just as mysteriously as it began, the road clears. There is no wreck, no police, no construction. The road is empty. You just lost 20 minutes of your life for absolutely no reason. Except there is a reason. You didn't encounter an accident. You encountered a mathematical inevitability. You survived a phantom traffic jam. It isn't bad luck. It is a failure of physics. And today, we're going to break down why traffic jams appear out of thin air and how physics, human reaction time, and control theory all collide to create them. Part 1. The invisible wave. To understand traffic, we have to stop thinking like drivers and start thinking like engineers. Traffic behaves less like individual cars and more like a fluid system. Each vehicle is a particle in a moving stream. When conditions are stable, the flow is smooth. But when density increases, the system becomes fragile. In a phantom jam, the cars are moving forward, but the traffic jam itself, the wave of stopped cars, is moving backward. This is a shockwave. It propagates upstream against the flow of traffic, usually at a speed of about 12 miles per hour. So, why does this shockwave form? It comes down to a fundamental conflict between how much space you have and how fast you want to go. This brings us to the most important graph in traffic engineering. Part 2. The fundamental diagram. To visualize the physics, imagine a hallway. We want to get the maximum number of people through that hallway in 1 hour. Engineers call this throughput. If there's only one person in the hallway, they can sprint at full speed. Their speed is high, but throughput is low. Now imagine a mosh pit. The hallway is packed shoulder to shoulder. Density is at its maximum, but nobody can move. Speed is 0, so throughput is also 0. Somewhere between the sprinter and the mosh pit is a sweet spot. This relationship is governed by the core identity of traffic flow. Flow equals density times speed. In engineering notation, Q equals K times V. Density, K, how crowded the road is, cars per mile. Speed, V, how fast cars are moving. Flow, Q, how many cars pass a point per hour. Flow is the result we care about. If we plot flow versus density, we get the fundamental diagram of traffic flow, an upside-down curve. At low density, adding cars increases flow. At high density, adding cars reduces flow. At the peak lies critical density, the exact point where the highway carries the maximum number of vehicles. Cross that point, and the system becomes unstable. But this curve doesn't come from a single magic equation. It comes from real data. Each dot on this graph represents one snapshot of a highway, how crowded it was, and how many cars made it through. Engineers collect thousands of these measurements during free flow, rush hour, and congestion. The smooth curve is just a best fit model, a simplified approximation of average behavior. Now let's make this concrete with a simple example. Imagine a 1-mile stretch of highway. We're going to measure how many cars get through it in 1 hour. Case 1. Light traffic. There are about 20 cars on that mile, and drivers can move freely at roughly 64 miles per hour. Flow equals density times speed. 20 times 64 gives us 1,280 cars per hour. Fast cars, but not many of them. Case 2. Moderate traffic. We add more cars. Now there are 50 cars per mile. Drivers slow down, but only a little, to around 40 miles per hour. 50 times 40 gives us 2,000 cars per hour. This is the sweet spot. The road is doing the most work it possibly can. Case 3. Congestion. We push it too far. Now we have 80 cars packed into that same mile. Merging, braking, reaction times, speed collapses to about 16 miles per hour. 80 times 16 gives us 1,280 cars per hour. Same road, more cars, worse performance. Each of these cases gives us a single dot on our graph. When traffic engineers collect real data, they get hundreds of dots like these. To understand the pattern, we need a model. One of the simplest is called Greenshields model. It starts with a basic assumption. As a road gets more crowded, average speed drops in a straight line. Fast when the road is empty, zero when it's completely jammed. If we plot that slowing speed times density multiplication, we get a curve, a downward opening parabola. Greenshield's equation allows us to estimate how traffic will behave given a couple of assumptions. For this example, we assume the road completely jams at about 100 cars per mile, and we scale the curve so the maximum possible flow is 2,000 cars per hour. That lets us estimate flow values at different densities, not as exact predictions, but as a smooth approximation of the trend. When we plot those points and connect them, the shape becomes clear. Low density, flow rises. Too much density, flow collapses. If we substitute the flow equation into Greenshields, we can approximate the second-degree polynomial that builds the parabola. That parabola, built from simple assumptions and real observations, is the fundamental diagram of traffic flow. Part 3. Braess Paradox. You might think the solution is simple, just build more roads. This brings us to Braess Paradox. Adding a new road can actually increase overall travel time. It comes down to game theory. Every driver acts in their own self-interest to minimize their personal travel time. If a new shortcut opens, everyone tries to use it. The shortcut instantly becomes a bottleneck that backs up the entire network. The collective result of everyone trying to save time is that everyone wastes time. Braess proves that traffic isn't just about total capacity. It's about how that capacity is distributed. Part 4. The latency chain and flow homogenization. Even on a perfect road, the flow is unstable at critical density. It's like balancing a pencil on its tip. One tap destroys the balance. Humans have a fatal mechanical flaw, latency. Our reaction time is roughly 1 second. This creates an amplification effect. Driver A taps the brakes. Driver B reacts a second late and brakes harder to compensate. By the time we reach driver Z a mile back, a slight tap has amplified into a complete stop. We aren't a rigid train. We are a loose chain of high latency agents. So how do we stop the collapse? We have to reduce variance. This explains those frustrating variable speed limit signs that drop the limit to 40 miles per hour when the road looks clear. This is flow homogenization. By forcing everyone to drive 40 miles per hour, we reduce the speed difference between cars. It is mathematically faster to move a solid block of traffic at a steady 40 miles per hour than a chaotic mix of 60 miles per hour and 0 miles per hour. The goal isn't individual speed. The goal is total system volume. Part 5. The control theory solution. The ultimate fix is control theory. In engineering terms, humans are over-damped responders. We panic and overreact. We need a system that is critically damped. This is where adaptive cruise control, ACC, comes in. It uses radar to maintain a precise time gap, acting as a shock absorber. We don't need 100% self-driving cars to fix traffic. We only need a 20% penetration rate. If 1 in 5 cars is an intelligent buffer, they can absorb the shockwave before it reaches the human behind them. Until then, you can act as the damper. Leave a massive gap and coast instead of braking. Stop the propagation. Traffic jams are both a failure of infrastructure and physics. We are trying to push something resembling a compressible fluid through a high-latency system. So the next time you are stuck in a phantom jam, staring at a saturated road, remember, you aren't just stuck in traffic. You are stuck in a backward-moving shockwave caused by a control system error 3 miles away. It might not get you home faster, but at least you know why. Thank you so much for watching. If you liked the video, please consider subscribing, liking, and sharing this video with others who are interested in simple engineering.